Hello students, welcome to this series on minimum spanning tree. So, what does minimum spanning tree means in the very first place? So, if you see, I have highlighted this minimum spanning tree with three different colors. So, starting with tree, what does tree means? So for example, your tree is nothing but a graph which has no cycles, right? So for example, a binary tree, which you might have known very well, is nothing but this is a graph and there is no cycle. But if I introduce any cycle in this graph, in this tree, it's no longer a tree, right? So a tree means a graph with no cycles. Second thing is spanning. So it is spanning. It is spanning something. What? Vertices of a graph. So there is a tree which is spanning throughout or spanning all the vertices across all the vertices of a graph. And then there is this term called minimum. So it seems that there are some spanning trees and we are interested in one of them, which we are calling minimum spanning tree. It seems so, right? Okay, so now let me give you an example, and with it would be more clear to you. Fine. So let's take this graph, right? And now let's take what the formal definition of spanning tree means. So a spanning tree is a subset of graph G. So for example, this is a graph G, which has all the vertices covered with minimum possible number of edges. So it means that that graph is just connected, right? Now, if you remove even a single edge, it will become disconnected. Okay, let me explain you with an example. So for example, this is your graph, right? Now, there are some cycles in it, right? You could clearly see this is one cycle, this is one cycle, this is one cycle, this complete is one cycle, right? Now, how do you remove these cycles? So the best approach is definitely by removing your unnecessary edges, right? So what I'll do here is, so for example, what I can do is, let me remove this edge, right? It is still a connected graph, right? So connected graph means all the vertices are connected, although we get into the formal definition later on. Now, are there still any cycles? Yes, there are cycles. You can see this cycle, you can see this cycle, this complete cycle. Now, let me remove one more edge. Any edge I can remove. So suppose I removed this edge. Now what? Is there a cycle? Yes, there is again a cycle. You can see this cycle, the complete cycle. Let me remove this edge also. Now what? You can see again that this graph is still, it is connected, but again there is a cycle. Let me remove one more edge. Now what? Now you can see there is something very peculiar. This graph is just connected, right? Now if we try to remove any edge, for example, let's say I removed this edge, the graph will become unconnected. You cannot reach from E to F. So it means I have to keep this edge. So visually looking, what I can say is that now this graph is basically a subset of graph G, right? Why it is subset? Because it has all the vertices, correct? And still it is a connected graph and has all the vertices covered with minimum possible number of edges. So this is the minimum number of possible edges. Otherwise, what will happen if I remove any one more edge? This graph will become unconnected. It won't be the same graph. So I hope you got an idea of what spanning tree is. Now, here we can also see that there is more than one way with which I could make this graph a spanning tree. So for example, this time I remove this edge, I remove this edge. Now still there is a cycle. I removed this edge, right? And finally I removed this edge as well. So from the same graph, this is also a spanning tree which we can obtain. Now, as you can see clearly, there are number of spanning trees which we can get from this graph, right? Now, what do we mean by minimum? Now comes the magic of minimum. So minimum will only come into picture if your edges have widths, right? Otherwise, all the spanning trees are same, right? So now suppose if I give this edge some weights, okay? So let me give it a weight, let's say 5, 10, 15, 20, let it be multiple of 5 only, 25, 30, 35 and 40. Now, again, if I am asked to make a spanning tree, I can make multiple type of spanning trees, right? But now, definitely, there will be a spanning tree whose edges, if I take the sum, will be minimum, isn't it? What it could be. So let's do a very simple thing. Let's start removing the edges with the maximum weight. I remove this edge. I removed this edge. No, this edge I cannot remove. Why? Because if I remove this edge, it will become disconnected. So this is the compulsion. I have to keep this edge. My bad here. Now what edge I can remove? Let's take the next higher edge. Can I remove this edge? Yes, I can remove this edge. The graph is still connected one. Then what? Then 25. Can I remove this edge? No, because if I remove this edge, F will become disconnected. Now 20. Can I remove this edge? Yes, I can remove this edge. Still there is a cycle. I have not given any value to this edge. Let me give it 17. Can I remove this edge? Yes, I can remove this edge. No, I cannot remove any further edge, right? So this graph, finally this spanning tree which I have made has to be minimum, right? Intuition is there, it has to be a minimum. So that's it. So this is the spanning tree. There could be another spanning trees as well, but if I sum the edges, if I take the sum of edges, it should be minimum. That particular tree is minimum spanning tree. Now you would ask that what are the applications, and by now you might have started getting an inkling or an idea that what are the practical applications of this minimum spanning tree. So let's again make this a tree. Let's again make this a graph once more, and this time let me have it 20, 25, 30, 35, 40 and 45, correct? Now see, in a minimum spanning tree or any graph, they can be, as I told you earlier also, there can be many practical application, because any practical problem can be reduced to a problem of graphs, right? So this very well could be a problem of, for example, connecting all these towns or villages in an area with electricity, correct? Electric wiring, right? So, and these the costs of each edge, which we can see here, it might be the cost of laying a cable, right, or setting up an electric wiring between these vertices, which in our case are towns or villages. So as an engineer, as an electrical engineer of a company, what will be your aim? Your aim would be to connect all these villages with minimum possible cost of laying the wiring, right? So what would you do? Definitely, as an engineer, what you try to do, because you have to make connection to each and every town, you will probably say that if I remove this, if I don't lay line here, right, fine, I still have the connectivity. Then you will say, okay, I won't go through this path. I won't lay my wiring along this path because it's very costly. Again, you can still connect all these towns, with electricity. Then what would you say? Next biggest. Now, if you remove this one, your D will be completely cut off from the grid. That you cannot do. It's a necessary evil, right? Then you'll say, okay, I take this also out. Cool. Then again, you cannot take this 15 out because then C and D will be cut off from the grid. Now, you could take 5, You could remove this edge, but then it won't be a cost-effective solution, right? Because this was your minimum. This was costing you the least. So what would be a practical approach? That you remove this one, right? And again, this is your spanning tree, and in your case, it is a minimum spanning tree, correct? And here you have a very good practical application of this algorithm. And when we'll study the history of spanning tree, we'll see from where it has come. It has very similar origins. Another example of intuition, another example of where spanning tree is very important. And in fact, one of the protocol is called spanning tree protocol is computer networks. So for example, if I again make the similar graph here, right? And now another application could be, as I told you, in the field of computer networks. Where? So for example, if this is a LAN network, right? Suppose if this is a LAN network and these vertices are your bridges, okay? These vertices are your bridges or switch, you can say, sorry. Consider them as a switch, okay? So these vertices are your switch. Now what happens is, that in case of this topology, there are cycles, right? So once a packet which enters into your network, right? So a packet which enters into a network will somehow, it's highly probable that it will continue to loop in this network. Now what's the downside of it? Downside of it is that ultimately, if there are 4 or 5 such packets, it will create a broadcast storm. So this is not a networking class. I'll not get into the details, but that broadcasting storm could bring the whole network down. So any loops in a LAN network is very lethal. So what the switches does now, making this, why we are studying this algorithm, now making this spanning tree manually for short number of vertices, it's relatively easy task. But suppose if your number goes high, maybe 200, 300 vertices, then it becomes totally, you need to automate this task, right? So spanning tree protocol does the same thing for your switches. So what it does basically, it tries to block off the links which has maximum cost, right? So what it will do is basically, looking at the cycle, it will try to block this edge. Block this edge means what it will do is block these ports. So these ports will come into a blocking mode. Now it will see, okay, now this is a necessary evil, because if we, okay, what was the cost here? I think it was 40, right? So yeah, so somehow it will try to calculate and see, okay, this is the maximum cost link. I'll switch it off. Correct. Now, which link? Definitely 30, right? So 30 goes off. Then which you can go off with to remove the cycle? Perhaps maybe 25, right? No. You cannot do away with 35, because once you do this, whole network will come down. Then not also 20, then you go with the 50. So again, so it somehow tries to block these ports and make a spanning tree. So you can see this is a spanning tree, and this doesn't have a cycle. So this is the applications and the intuition behind the minimum spanning tree. In next episode, we'll see its origin. We'll see that what are the 2 major algorithms, how they operate, on which programming paradigm they work upon, and try to build spanning tree using those minimum spanning tree, using those algorithms. Definitely pseudocode and time and space complexity will study in the subsequent lectures. But just to give you an idea that what minimum spanning tree is, how algorithms are building your minimum spanning tree, that we'll see in the next episode. Thank you very much.